Welcome to AI Paper Podcast, the show where we slice through the latest research papers. We try and extract the insights you need to stay on the cutting edge without getting lost in the weeds. Today, we're diving into something that could, fundamentally shift how we interact with text-to-image AI. Have you ever asked your AI image generator for something specific, only to get an image that's almost perfect, but just a little bit off? Maybe a stray arm or, a bizarre object in the background, and you just wish it could, fix its own mistakes. Well, get ready, because we're unpacking ReflectionFlow. This paper introduces a groundbreaking inference-time framework. What that basically means is it lets text-to-image diffusion models iteratively refine their outputs. It's like giving your AI an internal editor after it's already generated an image.
Exactly. And what's truly innovative about ReflectionFlow is that its core idea, it's directly inspired by self-reflection in large language models. Just as LLMs like GPT-4o and Gemini 2.0 can sort of think through a problem and correct previous generations for complex tasks, ReflectionFlow asks, can diffusion models do something similar, but for images? And it achieves this through a new concept they call reflection level scaling. This is powered by a brand new purpose-built dataset called GenRef. This whole combination helps models tackle those really tricky areas where current text-to-image systems often stumble. Think complex scenes, nuanced details, accurate human poses.
Right, we're getting multiple objects to interact correctly.
Exactly. And the big payoff for you, it significantly boosts image quality without needing massive, costly retraining of the base model you might already be using.
And that really is the aha moment, isn't it? This isn't just about tweaking an existing model. It's about changing how the AI approaches creation, moving from just a one-shot guess to a more thoughtful, iterative process. Kind of like how a human artist refines their work. Imagine getting dramatically better, more accurate images from the diffusion models you already use, just by adding this smart refinement step at the point of generation. So today, we'll unpack exactly how ReflectionFlow manages this, exploring its components and the pretty compelling results they found. We've all seen the truly incredible leaps text-to-image diffusion models have made recently. I mean, just think of models like FLUX.1 Dev. They're capable of producing stunningly high-resolution photorealistic images. It's genuinely mind-boggling what they can do now. But, despite this power, there's still this persistent challenge. When you push these models with requests for, say, complex scenes or really nuanced details, specific human poses, or compositions with multiple objects, they still often stumble.
They do. And traditionally, the answer to improve on that front has always been just scale up. More training compute, more data, exponentially more.
Which, as you can imagine, gets incredibly expensive and resource intensive very quickly.
Right. And that brings us to the core question this paper tackles. Instead of just focusing on scaling training, how can we unlock the full potential of the models we already have, but during the inference phase? Can we make them smarter, more adaptable with the resources we've got on hand? It's a really important parallel to draw with large language models, like you mentioned. We've seen LLMs use self-reflection techniques to dramatically improve outputs on complex tasks, like math problems or even code generation. So this paper directly explores if that same iterative self-correction idea can be successfully applied in the visual domain. Can diffusion models learn from and fix their own mistakes?
So, with that common frustration in mind, the AI almost getting it right, but not quite her. Our mission here is to explore ReflectionFlow. This isn't about simply training bigger models. It's about making the models we already possess fundamentally more capable, more intelligent at inference time through this iterative self-refinement.
Exactly. At its heart, ReflectionFlow is an inference time framework. That means it works after the initial model training is done. Its genius lies in leveraging iterative reflection. So instead of just generating an image in one go, it allows the model to progressively assess and refine its own output. The paper identifies 3 crucial scaling axes for computation at inference time, and ReflectionFlow integrates them really nicely. First, there's noise level scaling. That's basically searching for better initial noise to start the generation. This is a traditional approach, but it often hits diminishing returns.
Okay, so looking for a better starting point.
Right. Then second, you have prompt level scaling. This is where you optimize the input prompt itself for more precise guidance. You could almost think of it like having a multimodal LLM, an MLLM, act as your personal prompt engineer, refining your query on the fly.
Oh, okay.
And then the third one, the key innovation, reflection level scaling. This is where the framework explicitly provides actionable reflections to assess and correct previous generations iteratively. Imagine like a loop. An initial image gets generated, then a corrector refines it, a verifier checks it, and that feedback loops back. It creates this sequential chain of improvement.
What's particularly clever here is how it integrates all three of those axes, right? It lets models continuously improve image quality through this kind of dynamic, iterative process. It's basically a sophisticated feedback loop designed specifically for image generation. But here's the fundamental challenge you hinted at. Existing diffusion models, well, they just aren't built to interpret these detailed reflection prompts, are they? Or to effectively use a previous image as context for refinement. That seems like a big hurdle.
Absolutely. And that fundamental challenge brings us straight to the critical missing piece, and maybe the paper's biggest single undertaking. They needed a dedicated data set for this reflection-guided refinement. And this is precisely what the paper introduces with GenRef. It's the first large-scale image reflection data set out there. GenRef is really quite remarkable. It comprises, get this, 1 million triplets of data.
1 million, wow.
Yeah, each triplet includes a reflection prompt, a flawed image, and an enhanced corrected image. And it covers multiple domains, so it's quite versatile. The motivation behind creating it, well, it's rooted in the observation that self-refinement is conceptually kind of similar to image editing tasks. So the researchers adapted training methods used in image editing, things like instruct pic-supix, to help facilitate this.
Okay, creating a data set that specific and that massive sounds like a monumental task. What was the biggest hurdle in teaching an AI to reflect like this, and how did they even start gathering the right kind of data for this unique refinement process? It feels like a huge engineering feat just building this data set.
It really was. The key was developing a scalable, fully automatic data construction pipeline. That was crucial. This pipeline uses things like verifiable objectives, ensemble reward models, and diverse rollout strategies just to ensure the quality and the breadth of the data. They leveraged 4 distinct types of data for GenRef, everything from rule-based errors brainstormed by other AIs like GPT-4o.
So using AI to figure out common AI mistakes.
Pretty much. They intentionally introduced common flaws like missing objects or incorrect spatial positions, and then used other tools like grounded SAM to verify them. Then they had reward-based data where multiple AI judges scored image quality and alignment. They also had specialized editing data adapted from existing data sets like OmniEdit.
So a really diverse mix of error types and correction examples.
Exactly. This diverse approach was key to capturing the full spectrum of image imperfections and, importantly, their ideal corrections.
And building on that, they also created something called GenRef code, right? Chain of thought reflection. What's that about?
Right, GenRef code. This is a really crucial subset. It's 227,000 high-quality progressive annotations generated by powerful LLMs like GPT-4o and Gemini 2.0. This is where the models basically step-by-step analyze pairs of images, the flawed one and the improved one, and provide really detailed reflections. It's almost like an internal monologue for the AI, explaining why an image is flawed and how it should be improved. Seeing that kind of reasoning applied visually is fascinating.
That is fascinating. Almost like the AI showing its work.
Kind of, yeah. And to further ensure the quality of this massive data set, especially the enhanced images, they use a crucial step called Verifier Post-Processing. They trained an image reward model, basically, a super smart verifier AI, using a technique called Bradley-Terry pairwise comparison on that GenRef code data.
Bradley-Terry, that's like setting up tournaments between images.
Exactly. It's like having countless judges making head-to-head comparisons. The verifier is shown pairs of images and taught to consistently pick the better one. This makes it incredibly effective for teaching an AI subtle quality nuances. And it's then used to quantitatively evaluate image quality and filter out any lower quality samples. This verifier is absolutely crucial for the whole system.
Okay, so the data set is built, it's verified. What's next? Training the actual corrector.
Precisely. Was GenRef ready? The next step was training the corrector model. They treated this self-refinement task as a conditional generation problem. Their base generator was FLUX.1 dev, that powerful 12 billion parameter diffusion transformer we mentioned. Now, to efficiently fine-tune this massive model, they used a really clever technique called LoRA, or low-rank adaptation.
LoRa, right. We see that a lot now.
Yeah, it's very efficient. Think of it like adding a small, incredibly smart adapter to an existing engine, instead of rebuilding the whole thing. It lets them teach the model these new reflection capabilities without the huge cost of full retraining. They used a rank of 256 here. And a key architectural detail is the unified multimodal attention mechanism they implemented. The original text prompt, the reflection prompt, the flawed image, and the high-quality target image. They're all concatenated into a single sequence for joint attention within the transformer blocks.
Ah, so everything talks to everything else directly.
Exactly. It's really clever because it naturally facilitates information exchange across modalities without needing extra bulky modules like ControlNet, which are often used for similar conditional tasks. And for efficiency, they also downsampled the flawed images from 1024 down to 512 pixels before feeding them into the corrector.
So what does all this mean for the training strategy itself? It sounds quite sophisticated. I'm curious, why did they randomly drop certain inputs during training, like the original prompt or the reflection or the flawed image?
Yeah.
What's the point of that?
That's a great question. And it's actually a really smart move to prevent what they call distributional drift. Basically, it means the fine-tuning didn't make the model forget how to do its original job standard text-to-image generation.
Ah, so it can still work normally if needed.
Exactly. By occasionally dropping inputs, they ensure it can still perform well, even when it doesn't receive a reflection or a previous flawed image to work from. Plus, they used a task warm-up approach. They dynamically adjusted sampling probabilities from different data domains during training, starting with more editing data and gradually increasing others. This helps ensure robust instruction following while keeping that core visual quality high.
Okay, that makes sense. Balancing the new skills with the old ones.
Right. And that leads us to how ReflectionFlow actually uses this trained corrector at test time, during inference. It does this across those three scaling dimensions we discussed earlier. Noise level scaling, N, is the search with how many different initial noise samples you explore in parallel to find a good starting point. Then there's reflection level scaling, M, which is the reflection depth, basically, how many iterative refinement rounds an image goes through.
So N is width, M is depth.
Exactly. And finally, prompt level scaling involves using an MLLM to refine the text prompt at each round dynamically, based on the images generated so far and their evaluation scores.
Okay, so if I'm understanding this right, the actual ReflectionFlow algorithm weaves all these pieces into one continuous loop. You generate some initial candidate images, then an MLLM verifier evaluates them, generates those reflections, and maybe refines the prompts. Then that refined prompt and the reflection get fed to the corrector, which refines the images, and potentially this loops. It really creates a continuous chain of refinement.
That's precisely it. It's a very integrated process. And what's particularly advantageous is the flexibility this gives you. Users can adjust both the search width N and the reflection depth. You can balance performance against computational cost depending on your specific needs.
So you can dial it up for really important images or keep it quicker for less critical ones.
Exactly. It allows for a tailored approach depending on how complex the request is or how perfect you need the final output to be.
Right. Let's talk results then. How well did this actually work in practice?
Okay, moving on to the experiments. The setup used FLUX-but1 dev, that 12B parameter model, as the base, trained on their GenRef dataset. For generating the reflections themselves during testing, they used Qwen 2.5 VL7B, and for that crucial verifier role, they used Qwen 2.5 VL3B. All the evaluations were done on the GenEvol benchmark, that's 553 prompts, and they generated 4 images for each prompt to test consistency.
And the key finding, was it a noticeable improvement?
Oh yeah, quite stark. ReflectionFlow significantly outperformed simpler methods. We're talking beating naive noise level scaling, and even beating a combination of noise and prompt scaling. For instance, looking at runs with 32 total samples generated one way or another, ReflectionFlow hit a GenEvol score of 0.91. Noise scaling alone only got 0.85.
Okay, that's a clear jump. Definitely shows the power of integrating reflection.
Absolutely. And the choice of that verifier, the image reward model, it proved to be incredibly impactful. Experiments showed that using a general-purpose model like GPT-4o as a verifier, well, it hit its performance limits pretty quickly. Whereas their trained verifier, the one trained on GenRef, it demonstrated steady performance increases as the number of samples went up. And interestingly, the Oracle, the theoretical upper bound on GenEvol, showed a score of 0.98. That indicates there's still significant headroom. The framework itself has a strong ability to improve even further with better verifiers down the line.
That really underscores how vital that custom-trained verifier step is. It's not just about reflecting, but about accurately judging the reflections.
And what about efficiency? That was a big motivator, right? Avoiding massive retraining. Did ReflectionFlow deliver there? Hugely. This is maybe one of the most exciting results for practical applications. ReflectionFlow achieved substantial performance improvements using 10 times fewer samples compared to just naive noise level scaling, at certain performance thresholds.
10 times fewer, wow.
Yeah, it means getting those high-quality images much more efficiently, using far fewer computational resources.
Sure.
That's a genuine game changer for anyone actually deploying these models.
Definitely. That kind of efficiency makes advanced features much more feasible.
And another really interesting insight, one it shares with LLMs actually, is where it provides the biggest benefit. ReflectionFlow showed its largest gains on the most challenging prompts. For instance, on hard prompts, correctness just soared from 0.10 without reflection to 0.81 with it.
Huge.
Massive. For medium prompts, it went from 0.55 to 0.85, still very significant. But on easy prompts, where the base model's already doing well, the change was minimal, like 0.95 to 0.97.
Okay, so it really shines when the going gets tough.
Exactly. Which strongly suggests you could potentially dynamically allocate compute resources. Focus more refinement effort on the harder prompts that actually need it, instead of applying the same costly process uniformly.
That's smart. Smarter resource allocation. What about the strategy, deep versus wide? More reflections versus more initial guesses?
They looked into that with ablation studies. The results were pretty telling. Sequential strategies, meaning deeper reflection, more refinement rounds, higher M, consistently yielded better performance than parallel. Wider search strategies, higher N, given the same fixed compute budget.
So iterating is better than just trying lots of options once.
For the same amount of compute, yes. For example, a sequential strategy N1M16, so one initial sample, but 16 refinement rounds achieves a 0.78 score. Compare that to N16 M116 initial samples, but only one refinement round, which only got 0.74. It strongly confirms the value of that iterative correction process. Quality seems to come from careful, step-by-step refinement.
And beyond the numbers, what about the qualitative examples? Could you see the refinement happening?
Yes, and this is where it gets really compelling visually. The model doesn't just produce better images, it actually shows interpretable reflection chains. It's genuinely like a visual chain of thought, where you can follow the AI explicitly reasoning about visual inconsistencies or compositional errors step by step.
Like what? Can you give an example?
Sure, in the paper they show examples where the model gets instructions like reposition the bear, or add details to the guitar, or even something abstract like change the rabbit into a cheeseburger.
Okay, that's a weird one.
Right, but the model actually follows through, progressively correcting the image based on those reflections.
It's fascinating to see the AI thinking visually like that.
Wow, that interpretability alone is pretty valuable. Okay, let's try and wrap this up. What are the core takeaways here? Sure, to summarize the main contributions. First, they proposed ReflectionFlow, this inference time scaling framework that cleverly combines noise, prompt, and crucially, reflection axes. Second, they created GenRef, the first really large-scale image reflection dataset, 1 million triplets, plus those 227,000 chain of thought annotations. That's a huge resource in itself. Third, they developed an efficient reflection tuning method specifically for diffusion transformers, using LoRa. And finally, their extensive experiments validate the approach, showing substantial performance boosts, especially on those tricky, challenging tasks. It really unlocks a new level of reasoning capability for these visual models.
So looking ahead, what does this all mean for the future of AI image generation? It feels like a pretty significant step.
I think it is. This work offers a really promising direction for creating visual generation systems that aren't just more powerful, but also more reliable and adaptive. It represents a shift, perhaps, away from purely brute force scaling of model parameters. Instead, it moves towards smarter, more efficient refinement strategies, getting us closer to those perfect, on-demand images we're all hoping for.
Absolutely. It makes the AI feel a bit more like a collaborator, refining its work based on critique. So you've seen how ReflectionFlow empowers AI to reflect and correct its own visual errors, much like a human might refine a sketch. This raises, I think, a pretty important question for all of us working in or following this field. As AI systems get increasingly capable of this kind of autonomous self-correction, how might this impact things beyond just image generation? Could this lead to systems that can autonomously improve in complex real-world scenarios across all sorts of domains, not just art or visuals? What new challenges or maybe unforeseen opportunities might arise from AI models that learn to critique and refine their own creations at such a fundamental level? Something to definitely consider as you think about the next wave of AI innovation.